In this lesson, we will be discussing the dot product. We will be defining it and then seeing how we can use the dot product. The dot product is defined as a different type of multiplication between two vectors. So let's say we have vector v and vector w. Then their dot product is defined as multiplying a1 times a2, which means the I components, and then adding the product of b1 times b2. Now notice this is just a number, so the dot product is a scalar and it is not a vector. It is just a number. Now why do we call it a dot product? Well, if you remember from elementary school, when you first started learning to multiply, you wrote it as 5 times 2 like that. But then as you got older and noticed that that might look like an X, we changed it to sometimes a dot. Well, in vector land, those are two different types of multiplication. This one would be called the dot product. This one is the cross product, which we will cover in a future lesson. So let's go back to how to use, or let's just practice how to find the dot product. If we are given these two vectors, we want to find their dot product. So v dot w. According to this formula, we want to multiply the I components, so 2 times 4, and then add the product of the j components. So again, just really simple arithmetic, and that would equal to negative 13. Again, just a scalar, not a vector. Now one kind of cool property of the dot product is that if you dot the vector with itself, it's the magnitude squared. You may recall that the magnitude of a vector is the square root of the I component squared, I think we just called it a squared, and times the j component, or b squared. So let's see if I dotted the vector with itself. So let's take vector v here, and I want to say v dot v. What's going to happen? I would say 2 times 2, the I component times itself, plus 3 times 3. Well, hopefully you can see that that's a squared plus b squared. We just haven't taken the square root, and that's why the if you dot a vector with itself, you get its magnitude squared. The dot product can also be used to find the angle between two vectors. So looking at this diagram, if you have u and v with an angle theta between them, the cosine of that angle is found to be the dot product divided by the magnitude of the two vectors, and theta is between 0 and 180 degrees. Now where that formula comes from is from the law of cosines. And if you would like to see that formula derived, take a minute and go to this video. Let's look at our second example of how that's asked us to find the angle between the two given vectors. I've given you some graph paper just so you can look at it on a graph. So I'm going to take an XY system and go ahead and graph V. That's also good practice. So V is, so if I take that to be the origin, over 2 and up 3. So that's vector V. And then W would be over 4 and down 7. And what I'm asking you to find is that angle right there, theta. So there's a couple of different ways to do it. The easiest way, I think, is to use that formula. So that formula says I need to know their dot product and their magnitude. Well, we did just find their dot product in the previous example. If you look up here, I believe those are the exact same two vectors, and so their dot product is negative 13. So v dot w is negative 13. Remember, 2 times 4 is 8. 3 times negative 7 is negative 21. We added those together. I also need to know the magnitude of each vector. So remember, the magnitude is the square root of the I component squared, the j component squared. Adding that together, I'm going to get 4 plus 9 is 13, so that's the square root of 13. The magnitude of w Again, the I component squared, the j component squared, and I believe that would be 16 plus 49, which is the square root of 65. Alright, so now I want to find the angle between the given vectors, theta. So let's start out with that the cosine of theta is the dot product divided by the magnitude of v multiply the magnitude of w. Now you want to be careful punching that into the calculator. Right, so I would have the cosine, I'm just going to do this calculation. This is negative 13 divided by, and you could do 1 square root of 13 times 65. The cosine of theta is approximately, again, punching that into the calculator, is negative 0.4472. Now leave everything in your calculator, and we need to know theta. So theta is the inverse cosine, and if you have an answer button, you could say answer, or if you rounded, that's okay. And so theta ends up being 116.6 degrees. And you can see that that is a reasonable answer. That definitely was an obtuse angle. Now we're going to look to see, are vectors parallel, perpendicular, or neither? One way to determine if two vectors are parallel if the angle between them is 0 or 180 degrees, which makes sense. Remember, parallel lines have the same slope, so vectors, if I have two vectors, and I superimposed them on top of each other, moved this one down here, the angle between them, of course, would be 0 degrees. And they would be parallel. But if I had one vector going that way and one vector going that way, and again kind of superimposed them and put this one over here, that angle is 180 degrees. Now what would be helpful to know, remember our cosine of theta, that angle between them, that what is the cosine of 0 degrees? Well, the cosine of 0 degrees is 1, and the cosine of 180 degrees is negative 1. So basically they're parallel if this result, u dot v over their magnitudes, is equal to 1 or negative 1. So let's look at example 3. We're going to determine if these two vectors are parallel. Again, you don't have to graph it. I just think that sometimes looking at a picture will help you go, ah, I understand that. So let's just sketch those graphs. And let's see, vector v over 3 and down 1. And then w is over 6 and down 2. And since these are position vectors, meaning that they both start at the origin, you can kind of see that they're parallel, right? They're just an extension of each other. But let's just verify that. Let's just go through the math. So I want their dot product. So u dot v is 3 times 6, remember multiplying the I components, and then multiplying their j components. So let's see, that's 18 plus 2, that's 20. The magnitude of v would be the square root of 3 squared, negative 1 squared, which would be the square root of 10. And the magnitude of u would be 6 squared and negative 2 squared, which I believe is the square root of 40. So if I did that math, u dot v, that's 20, divided by the square root of 10 times 40. Since they're both under the square root, you can put those together. So let's see, we'd have the cosine of theta equals 20 over the square root of 400. Guess what the square root of 400 is? That's 20. That's 1. So what's that angle? 0 degrees, which of course we saw from the picture. So are they parallel? Yes, they are. Well, if we have parallel, we also have perpendicular. But in vector land, we don't call it perpendicular. We use the word orthogonal. But that also means perpendicular, which means forms a 90-degree angle, right? So when we're looking back at that formula here, we would be nice to know, what is the cosine of 90 degrees? Well, you know, it's 0. So if I replaced 0 in here and did some math, let's say if I cross multiplied, 0 times anything is 0, and 1 times that, two vectors are orthogonal if their dot product is 0. So let's look at this example and to see if they're orthogonal. And again, I've given you a picture that if you wanted to sketch it out, just to see visually. So we have, that's V over 2 down 1, and then W is over 3 and up 1, 2, 3, 4, 5, 6. Now that looks orthogonal to me, but let's prove it. All we need to know is their dot product. Is that 0? So we'd have 2 times 3 plus negative 1 times 6. That is 0, so yes, those two vectors are orthogonal. The next thing we're going to do is we're going to take a vector and decompose it. We're going to break it apart into components. Now you're going, well, we've done that before. Yes, but those were vertical and horizontal components. What if we wanted it compared to not the x and y axis, but to another vector, say w? So what we're going to do is we're going to take a vector v, some angle, and we're going to project it or break it apart into components according to w, which means we're going to drop a perpendicular. So we're going to look at that vector v1, so that's going to be parallel to w. And this vector v2, that's going to be orthogonal or perpendicular. And hopefully you remember from graphing the vectors that v1 plus v2, remember tail, head, that's going to be the addition, that's going to be the resultant vector. Alright, so how can we get those parts? Some pretty funky formulas, but the part that's parallel, or we would say the projected part, meaning v, if we kind of took a light and shone it directly down, what shadow would it make? What would it project onto w? What part? That would be this part. And yes, you need to memorize that formula. And then once we have v1, we can get the second part by just simple subtracting by using that. So let's go through this example. Find the vector projection of v onto w. In other words, decompose v into two vectors. All right, so just using those formulas straight away. All right, so v1, what do I need to have? I need to have their dot product. So let's hold on to this for just a second. Let's go through those steps. All right, so what is v dot w? Well, we're multiplying. So that's 1 plus 3, that's 4. That's their dot product. What else do I need? I need the magnitude of w squared. All right, so the magnitude is a square root, but if I square it, that's going to go away, and we would have 1 squared plus 1 squared. Right? So that goes away, so if 1 plus 1, that's 2. This part is a scalar. This part is a vector. So we're going to multiply a scalar times a vector, which we certainly are allowed to do. So v1 is the dot product of 4 divided by the magnitude of w squared, which is 2, multiplied by the vector w, which is I plus j. So v1 is just 2 times I plus j, or you could write it as 2i plus 2j. That's a vector. That's the part of v projected onto w. Now we need to do v2. Well, we're going to look at that. So v2 is just the vector v subtracting the answer we just got. So v was I plus 3j, and I want to subtract the answer I just got, and again, that's just collecting like terms. So I minus 2i is negative I, and 3j minus 2j would be 1j. So we have found V1, the part that's parallel, and V2, the part that's orthogonal. Again, that's called a vector projection. Let's just go through one more example. Okay, you're looking at your formula. So, I'm not going to confuse you by using different letters on the test. I'm going to keep it with V's and W's. So I need to know the dot product. I need to know the magnitude of W squared. So V1, those two numbers divided, multiplied by the vector W. So that's just going to be 4/5 I minus 8/5 J. The part that is orthogonal, I need to do some subtracting. Okay, so we have some fractions to deal with. Right, so I'm going to have 2 minus 4/5. That's going to be in the I direction. Then I'm going to put plus, and I'm going to have a -1 from here. Minus a minus is plus 8/5 in the J direction. Just showing you where those numbers come from. Find a common denominator, subtract. So let's see, that's going to be, I believe, 6/5 in the I direction. And then that would be positive 3/5 in the J direction. So not complicated, just keep in mind that the dot product is a scalar. Where does this formula come from? Well, we're going to derive it. It comes from the law of cosines, which is similar to the Pythagorean theorem, a squared plus b squared equals c squared, but because the law of cosines applies to non-right triangles, you get that extra little 2ab cosine theta at the end. Well, let's relate this picture over here to my law of cosines. So I'm going to call this side C, this side A, and this side B. So rewriting that in terms of the law of cosines, I would have u minus v magnitude squared equals magnitude of v squared, u squared minus 2 times uv cosine theta. Well, so I've got a cosine and I've got some magnitudes, but where does that dot product come from? Earlier we learned on the dot product that if you dot a vector with itself, you get the magnitude squared. So I'm going to replace this using the idea of dotting it with itself. So let's take u minus v squared and write that as u minus v dotted with itself. And I'm going to go ahead and put little arrows above this just to remind ourselves that those are vectors. And so now I'm just going to use the FOIL process. So I'm going to have u dotted with u minus 2u dotted with v. And that 2 came from u times v and v times u. Then plus v dotted with v. I'm going to come back up here and use the idea that if you dot a vector with itself, you can rewrite that as the magnitude of the vector squared. So what I am looking at is I'm trying to replace this with that. That's exactly what I'm going to do. So I'm going to come back up here and I'm going to take this left-hand side and replace it here. So that's what the u minus v magnitude squared equals to. Now I'm going to use that part of that formula. Now let's look at some algebra. Can we start kind of collecting like terms? I think so. I have this and this on both sides, so if I subtract it, it's going to add to 0. Have this on both sides, same thing. So now what's left? They both have a negative 2, so I can divide by that. And look at there. There's that dot product. So I could solve for the cosine of theta and say, yes, indeed, it is the dot product of u and v divided by their respective magnitude. And that is where that formula comes from.